Okay, so we've covered probability distributions, functions that take input values of x and that tell us about the probability of the random variable x taking specific values. And so visually, here's an example, the log normal distribution. Excuse me. It's a distribution with two parameters, mu and sigma. In this plot, on the y-axis is the value of the probability density function, and on the x-axis is the x values, the specific values that random variable x can take. And so that's what a probability distribution does. We input values of x and it outputs probabilities. In the discrete case with a probability mass function, it does that directly, plug in x to the formula, and out will come the probability of x taking that given value. In the case of continuous random variables, as we explained, it has to be done via integration to find the probability that x takes a value in a given range. Now, as we've seen, probability distributions take different shapes. That could be because they're from different families. So the exponential family, exponential distribution, has a different shape than the normal distribution. And they also take different shapes within the same family as the parameters of the distribution change. So the question we now want to ask is, how do we describe or capture, how do we summarize the characteristics of a distribution and their shape? And the way we do that is through quantities known as expectations and moments. Quantities that allow us to describe the characteristics and shape of probability distributions. So what they're trying to do is capture useful partial information about a random variable, and we'll look now at some specific examples, deal first with the concept of expectation and then move on to that of moments. Now, an expectation is a key concept in probability and statistics. You will know it as the mean. So the expectation of a random variable, or its expected value, is the average value or mean weighted according to its probability distribution. So expectation you can think of as providing a measure of the centre of a distribution, okay, which via probability weighting summarises a typical or expected value. So we'll define it here in this definition 18. For discrete random variable x, the expected value or the mean of x is defined as the sum of the x over all possible values of x times the probability of obtaining that particular value as given by the PMF. Okay, so that is the expectation in the discrete case. And the notation for expectation is this letter E that we're going to use in this double form. So that's the notation for expectation. For a continuous random variable x with a PDF fx, the expected value or mean is exactly the same principle, but this time, of course, we're going to have to use integration because we're dealing with a continuous random variable. So it's the integral of x times the PDF of x over all possible values of x, which again gives us the probability weighted value. The average value weighted according to the probability distribution. That's what this integral is going to give us. So properties of expectations, they're summarised in this slide here and they're very simple. Let g be a real valued function whose domain is the range of x. Then let's think about the expectation of gx, the function of x. Now we're looking at a function of x just to generalise these properties so that it doesn't just apply to the random variable itself, but any function of that random variable. But of course, if that function was the identity function, then this just reduces to the random variable itself. But the expectation of this function of x, gx, is given in the discrete case by this quantity here, gx times the probability density summed over all values that x can take. And in the continuous case, the integral of the same, gx times the PDF integrated over all possible values of x. So the key properties are very simple of expectations. The expectation of a times g of x plus b times h of x, where h is some other real valued function, is equal to a times expectation of g of x plus b times the expectation of h and x. And Those properties of expectations simply follow, of course, from the rules of summation and integration, so there's nothing complicated here, and there's a little proof given here that you can look at in your own time just to verify that you're happy with those properties. Okay, so that's expectation. I now want to introduce a closely related concept. Moments are an important class of expectation. In a sense, you can think of them as a generalization of the concept of expectation that provide information about the shape of a distribution. So with moments, we're able not just to describe the central tendency of the distribution as we do with the expectation itself, but we can talk about its shape. And we'll go through some definitions here and just briefly summarize and then look at what moments actually are with respect to a specific distribution. So, definition of moment. For each integer k, the kth moment of x is defined as the expectation of x to the power of k. And the notation that we use for moments is u prime. And given what we've just said about the rules of expectation for a function of x, then the moments must take this form here in the continuous case and must take this form here in the discrete case. And of course, if we set k equal to 1, then the first moment of x is simply the expectation in both the continuous and the discrete case. Next definition for moment is what's called a central moment. So if we write that mu is equal to ex, a constant that doesn't depend on x, okay, so this is just the parameter of the distribution, so to speak, it's the first expectation of x, then the kth central moment of x is equal to, notation here, mu k but not with the prime, is equal to the expectation of x minus mu to the power of k. And again, by the rules of expectation, in the continuous case, this quantity is defined by this integral here, and in the discrete case, by this summation given here. Okay, and the final definition of moment, standardized moments. In this case, we're going to write sigma k as the expectation of x minus mu to the power k. Then we define the kth standardized moment of x as this quantity here, and this time, for notation, we're going to use tilde to denote a standardized moment, and it's equal to the expectation of x minus mu over sigma to the power of k. Again, rules of expectation dictate that this quantity here can be written in this form. Now, those definitions are important, but really, more than that, what I want to get across to you is that moments are able to provide information about the shape of a distribution. And there's 4 commonly calculated moments, and I'm sure that most of you will have heard of them before, that allow us to describe the shape of a distribution. The first moment is called the expectation, denoted ex, and that gives us a measure of central tendency. It's measuring the centre of a distribution. The second central moment, expectation of x minus mu squared, so second because k equals 2, is called the variance. And the variance measures the dispersion of the distribution. Okay. The third standardized moment is called skewness. Okay. This formula here, it's the third, so k equals 3, and this measures the symmetry of the distribution. And the fourth standardized moment, called kurtosis, power of 4, k equals 4, measures the tailness of the distribution. So just to give an example, here we have the normal and the log normal distribution. This is the normal distribution. This is the log normal. Mu is the first moment. That is the expected value of the distribution. In this case, we have 3 normal distributions where the expected value is 0, and therefore the expected value sits right in the centre of the distribution. So the expectation is telling you about the centre of the distribution. This case here, we've set mu equal to 1, and so the centre of the distribution is lying over 1, not over 0. So the normal and the log normal distributions, both of these are defined by 2 moments or parameters, mu and sigma square. Mu, the expected value of the distribution, controls its location, or its central value, and sigma squared, the second central moment, controls the spread or the scale of a distribution. This is the variance. Now, the normal distribution is symmetric about its mean value, it's symmetric about its expected value, and that means it has zero skewness. It doesn't have skewness. Its third standardized moment is 0. The log normal distribution, on the other hand, you can see does have what's called a right-hand skew, so the distribution is skewing out to the right-hand side and its skewness is greater than 0. So this is just to demonstrate how moments, what they tell us about the distribution. In this case, the mean is telling us how the distribution shifts in that direction, the expected value. The second central moment is telling us about the spread of the distribution. Is the spread quite wide, as in the case of the yellow one, or less wide, as in the case of the red distribution? And the skew is telling us about the actual shape of the distribution in terms of how it's pulled out towards the right-hand side. Now, I said that the second central moment captures the variance, and this is a very important moment in statistics. It's got a lot of, it's talked about all the time, the variance. It has very important statistical properties that we're going to use. And the variance is defined by this expression here. As I said, it measures the spread or dispersion of a distribution around its mean, which means that small values of variance mean that x tends to be quite close to its expected value. The random variable x is closely packed around its expected value. Large values of variance mean that x is more variable. You'll find values of x further away from the expected value or the mean. The positive square root of the variance is known as the standard deviation. It also measures spread, but it's often used or preferred to the variance because the variance is a squared quantity. So taking the square root of the variance puts it back in the same units as the random variable itself, so sometimes can be easier to interpret for that reason because the units are back to that of the random variable. The properties of variance are given in this theorem here. If x is a random variable with finite variance, then for any constants a and b, the variance of a times random variable x plus b is equal to a squared var x. So all we're saying here is, first of all, adding a constant to a random variable doesn't change the value of its variance. Multiplying a random variable by a constant a requires us to scale the variance of that random variable by a squared if we want to calculate the variance of a times x. And there's a little proof given here so that you are happy that those properties are indeed the case. Okay, in this slide I've included an alternative form of the variance so that you can derive actually from the rules of expectation. This is sometimes preferable, it's sometimes easier to use. You'll be able to establish this in your own time, but I'm just putting it here because we may use it elsewhere. Okay, and the final thing I want to cover in this part of the lecture, and I mean this is mainly really for reference, is the concept known as a moment generating function. Now, we know that we can characterize distributions by either PDF, by either CDF or PMF, PDF, or by a CDF. A moment generating function offers an alternative way to characterize a distribution, and it's important in theoretical statistics really, where some really important results are easier to derive using a moment generating function. We're not going to use it extensively in this course, but I do want you to know what it is. And of course, as the name would suggest, a moment generating function can be used to compute moments directly. So the definitions here for random variable x with a mass or density function fx, the moment generating function is defined as that quantity there. It's the expected value of e to the power t of x. So remember, by the rules of expectation, this is a simple thing that must take this form in the discrete case and must take this form in the continuous case. Now, in terms of moments, the MGF has a property that the nth moment of random variable x is equal to the nth derivative of the moment generating function when we evaluate it at t equals 0. And if you just play around with these quantities here, you'll be able to prove that yourself. We don't need to go through the proof here, it's not so important. I just want you to know that it is possible to generate moments for the PDF by repeatedly differentiating the moment generating function. Sorry, it's possible to derive the moments of a random variable from the MGF by repeatedly differentiating the MGF and setting t equal to 0.